I'm planning on talking about big analog data, which was in the description. I was approached about coming to this conference approximately 6 months ago. I agreed to do it, very excited about it. It's my first time here, and I've enjoyed my time. I'm going to go through really two large sections of the presentation are going to be around some customer case studies where people are implementing industrial Internet of Things solutions. Firefly Equipment is a small agricultural company, a provider of agricultural equipment. London Underground, of course, is the subway system in London. And then Innovare is a small enterprise that's doing smart grid solutions for emerging markets. Now, if we look at those case studies and how they're implemented, they all follow a very similar architectural pattern. So I'm going to dig into the similarities of the architectural pattern at the system level, but then also down at the edge system level as well. And then talk about some of the approaches that were used and some of the benefits that can be extracted from those approaches as these systems are built. And I actually am planning on doing a demo. So we'll see how that goes. So it says, got a little bit of everything. When Amin, set this up, I agreed, and then I looked at the agenda and I saw 90 minutes. I'm like, okay, this better be good. So I got to keep these people interested for 90 minutes. I gotta really bring it. So, and I think we've got a good discussion. But the Phil Donahue point is, this can be as interactive as you guys want it to be. Stop me at any moment. Feel free to ask a question. This isn't intended to be a one-to-many presentation. It's intended to be interactive. If there's something that's unclear or you think there's a point that deserves more discussion or exploration based on something else you've seen at the conference or a challenge that you've heard from elsewhere, expose it to the room, because it's probably, I'm going to hazard a guess that I'm not the smartest person in the room. Bet you the smartest person in the room is someone else. And if we all sort of put our brains into the discussion, probably everyone will get more out of the discussion. All right. So with that, hey, okay. I think I hung the computer already. Now, so the industrial, my role at National Instruments, that's a company I work for. How many people have heard of National Instruments? Okay, about half the people. So we're a 40-year-old company that does hardware and software that's targeted as tools for scientists and engineers to make measurement and control systems. So if you're testing a cell phone, or you're testing the software on a car, or you're implementing a smart grid analyzer or a machine controller, our products are used across all those industries. Now, my area is on the industrial focused products. That's what I work on. And because our systems are very using very intelligent systems and they're all networked, we've been kind of organically pushed into this industrial Internet of Things space. And customers are building these systems. We even have some really great examples of what I would call state-of-the-art industrial Internet of Things solutions, and the people building them have no idea that's what they're doing. Right? They're building a system to solve a particular problem or meet a need, but it has all the elements that are talked about in the IIoT writing or the Internet of Things writing, if you prefer. Now, this is something that may be news to some of you, but there's a belief, a very broad belief, that the consumer IoT is a great economic opportunity for companies like the multimedia companies and Fitbit and people making cameras with radios on them and what have you. But the real economic impact is going to be the industrial Internet of Things, the type of productivity gains that Joe was talking about during his talk, the $1 to $15 trillion of additional productivity to GDPs around the world. And the World Economic Forum, in a paper that they released, it's actually now, it's almost exactly a year old. It came out in May. It actually is a year old. May of last year. It's available online. You can read it. One of the quotes from there is that they came to the conclusion that the industrial Internet will dwarf the economic impact of the consumer Internet of Things. Okay. All right. Now, as people build out the industrial Internet of Things, the concept around data and big data, we believe, is going to shift. Okay, this visual is not intended, it's intended to be conceptual. And you can see down here this gold bars is intended to represent structured data. This is like operational data, customer data, IT data, those sorts of data sources that are structured, very well organized. There's this concept of unstructured analog data that's coming from sensors. I had a conversation with someone today that's working towards the concept of very intelligent light fixtures. And these very intelligent light fixtures are going to produce enormous amounts of data. The customers that I'm going to talk about are already producing enormous amounts of data. That's because the physical world around us is a source of infinite data. It is completely unbounded. And at NI, we call this the big analog data. Now, how do you people, again, if the questions seem fundamental, and I don't want them to come off as seeming too fundamental, but I've had people get confused. Is everyone in the room familiar with the concept of an analog to digital converter? Some nods. Okay, everybody's nodding. Okay, so the idea that you have a sensor or a voltage that goes in, and then coming out of that component is digital data. Of course, all the data that we're talking about is in the digital domain, but it's coming from the physical world through sensors. So we're not talking about storing and processing data in the analog domain, but the source of the data is analog, whether it's vibration data from a machine that's vibrating, or data around light intensity, or data from a camera, or sound. Those are all sources of analog data. And it is truly infinite. It's only bounded by the number of sensors we install, the resolution we use, and the speed at which we use to acquire the data. Okay, I want to show an example here to kind of get the point across. Here's the concept of a wind turbine, and people have been doing condition monitoring or predictive maintenance for years on industrial equipment. Here, with this example, this is sample rate, might be a little hard to read, and these little ticks are intended to represent a particular rate at acquiring data. If you acquired a particular rate, you'll get an analog signal, and if you process it, you may determine that there's an imbalance in your wind turbine. So things are not operating as perfectly as they could be. But if you increase your sample rate and perform additional analysis on the data, you might not only realize that there's an imbalance, but there's also a particular bearing that's about to fail. And with additional prognostics and more accurate measurements, you might even be able to determine exactly when that failure is going to occur. And then you can handle your maintenance scheduling, you can order parts, and really do predictive maintenance instead of preventative maintenance on this piece of critical equipment. And that's because we're combining high-speed analog measurements, in this case vibration, with analytics to determine that the system is going to fail, and then how it's going to fail. Okay? And so that's one example. Now you could say, well, it's easy. The problem's easy. All we got to do is just put a bunch of sensors out there in the real world and then just connect them to the cloud. Problem solved. Okay. Now, we have to remember that in the physical world, the potential data source is infinite. And so we can't just connect sensors to the cloud and push all that data up into the cloud and do prognostics and predictive maintenance and advanced analytics on it using a cloud platform from one of the great cloud platform providers, some sort of cloud service. Well, because there just won't be enough network bandwidth. Network bandwidth is going to increase over time. But what we need to do is add computation in between the sensors and the cloud. And ideally, a form of computation that's heterogeneous, that uses maybe processors plus FPGAs to process and massage that data before it then gets connected on to another system or maybe the network and onto the cloud. Yeah, please.
You're talking about sensors producing data. There's no notion of control of the sensors
In this particular example, no. Some of the customers I'm going to talk about, control is a big part of what they're doing. But here, just fundamentally, we're just starting with just acquiring the data, processing the data, and then making decisions based on that data. Okay? Does that make sense? Pretty foundational. Now, ideally, there would be an architecture and there'd be tools that would allow you to implement these systems that allow you to interact with the real world, bring in sensor data, and potentially control actuators to interact with the physical world. You'd be able to process that data to do control loops or, decimate the data down to smaller data form, massage the data, pull out key data features, whatever's important, and then through some sort of connection, connect it onto another machine or up to the cloud. And we can't afford to do a point solution for every type of system or asset. We couldn't do an independent architecture for wind turbines and then implement a completely separate architecture and separate approach for agricultural equipment or the power generation facility that's using fossil fuels or medical systems and so on, and cars and trains. We want to have some architectural consistency across these systems so it's easier to integrate them into a system of systems. We build this out. And if we do this right, you'd be able to acquire significant amounts of data from the edge, massage it down and push it into the cloud for advanced analytics, and then once you've learned about the behavior of the systems, you can push that analytics back down to the edge and have the systems themselves extracting those features and trending and making decisions about their own health and their own behavior. All right, so now what I'm going to do is I'm going to shift gears and go into 3 case studies. But before I do that, I'll open it up to see if there's any fundamental questions about conceptually what we're talking about sensors, computation, and connectivity. Yeah. Okay. Why don't you have a repeat the question? I'll repeat the question for you. The question is, so we're recording, but I'll repeat it for you. So we're recording the session, so I'll repeat the question or we'll do the question into the mic. So the thousands and thousands of people that come back and watch this session will get all the context. Yeah, okay, good. Perfect. Okay, all right, so we are talking about doing whatever analysis or analytics is appropriate. So it starts with acquiring the data and getting it into the digital domain, but a simple form of analysis that you might do is move things from the time domain to the frequency domain by performing some variant of an FFT on the data. Then you might, window the data and then look for the peak frequency and get the amplitude and the frequency of that peak. That all might happen in the analysis portion before you sent any data on to the cloud. So that would be an example. So it can be inclusive of simple analysis such as that, as well as more advanced analytics. A very good question. Okay. So I'm going to talk about any other questions before I move into first case study. Yeah. Yeah. Mm-hmm. Sure. So if I understand the question is, of course, we start with raw data, and then you start with processing the data. Now, the visual I showed, I'm not sure if you were here when I showed the wind turbine and the vibration data on the wind turbine. So, and I'll just go back to that visual. My PC's a little finicky. It's time to upgrade. So if we go back to the visual, just to make the point, the raw data in, it's going to be 2 more clicks. I just don't want to go past it. Okay, so the raw data in this case, there's an accelerometer on the wind turbine that's measuring vibration. So the raw data is an incredibly rapidly changing dynamic signal that if you visually look at it with your eye, you get no meaningful information from that data. Okay. If you zoom in, you would see maybe some sort of periodic sine wave with some sort of vibration on top of it, higher frequency components. If you perform analysis on that data and convert into the frequency domain, you can start looking at the frequencies where there's vibration as well as their amplitudes to start to learn more about what's happening with the system. So the raw data is vibration, the process data is frequency of that vibration. And then if you go even further, you can start doing advanced pattern matching on that data and matching it to learned patterns through machine learning and do advanced prognostics. It's kind of like the next step. Did I answer your question? Okay, great. Okay. All right, so now I'm going to step into the Firefly case study. So Firefly Equipment is a relatively small organization out of Utah, in the United States, and they provide agricultural equipment. Specifically, what they provide is they provide sod harvesters. So these are machines that harvest sod, grass, that gets sold to golf courses, home and garden stores, so we can put it on our lawns, football fields, soccer fields, cricket fields, whatever your sport of choice is. And this particular piece of equipment is called the ProSlab 150. I think we'll see it in a minute. So the ProSlab is a relatively contemporary piece of agricultural equipment, and it's connected to the internet. So I'm going to walk through and talk about some of the things that they did in building the system to try to optimize the system, but then talk about some of the benefits they get by making this into a smart IoT device for their small enterprise. Okay, first, this particular piece of equipment adds value to their customers, and their customers are farmers. These are people that grow grass and sell grass. They're not technologists. And the ProSlab has an overall benefit to their farmers of roughly 2x. They get double the cutting of grass or harvesting for the amount of capital expenditure and operational expense of running the machine as previous machines. It runs faster, and it uses half the fuel. And then there's other benefits that it can cut any type of grass, and it also stacks the grass better so it can immediately be shipped to the reseller or the wholesaler or what have you. Okay, so if we take a look at the guts of this thing, they've centralized all of their control of this machine into a single controller that runs 30 parallel control loops. So here they're bringing in sensor data as well as network data, making measurements, doing advanced calculations, and then controlling the systems. They're controlling a hydrostatic transmission as well as many servo valves on the particular machine. But by consolidating all of the I/O into a centralized controller, they have dramatically simplified their system design. Many of these systems, the way they're implemented, is a bunch of distributed controllers. If we think about some of the cars we drive, if somebody here is driving a Tesla, you have roughly 100 processors in that particular machine. It's a very distributed control system. But here they made the decision to consolidate as much as they could in one controller to simplify the system design, and then focus on tuning the system itself and these control algorithms. That's how they got the reduced fuel cost and the increased speed, increased performance, by continuing to tune their control system and simplifying into a single controller. But the controller they chose was running a real-time version of Linux. And because of that, because it was a contemporary operating system, they were able to relatively easily connect it to an LTE modem provided by AT&T and get it on the internet. Okay, if they would use a historical real-time operating system, it's very difficult. Excuse me, I hit the wrong button. It's very difficult to add device drivers and advanced connectivity to those systems. But Linux itself, similar to Windows, Linux has a very vibrant ecosystem. I think many of you probably realize that. And so by being able to connect it to a serial modem, they're able to open up benefits of having a connected, distributed, smart system that they could sell anywhere in the world. And so from their little facility, I don't want to, their facility, they're not that small, but they're not John Deere, they're not Caterpillar, right? They're a smaller provider. They're able to connect to their harvesters wherever they are in the United States. They also have customers in Australia and South America and Europe. So because this thing is connected, they can do a variety of things with the system. One, they can pull data back to determine the health of the system. Is the soft harvester operating correctly? They have all of those 150 sensor channels going into one controller. They can choose what data gets passed up to their centralized offices in Utah and do trending on that data. Okay. They also can push software updates to these machines. If they find that there's a particular way that they can tune the controller better to make it more efficient, they can push that out. Not that different than what Tesla does, right? They make your car smarter every day, I guess. And then they can also train the farmer. Let's remember that these people that are growing grass and cutting grass, they're not here at the SATURN conference with us, right? They have different skills than the people here. And to bring up a sophisticated computerized system such as this, they have three choices. They can have it connected so they can do it remotely, which is what they did, or they'd have to fly a technician to where they sold the system, or they'd have to train a distributor so that distributor could train the farmer. Options 2 and 3 are very expensive and would fundamentally change where they could sell their systems or the price that they could charge for their system. Okay. Sure I didn't miss any. So fundamentally lowers their operating expenditures for their product, and it allows them to be able to serve the entire world from their offices in Utah. Okay. So if we sort of summarize that, this visual is going to appear a few times for each of the 3 case studies that I'm going to talk through. They had their thing, which was their sod harvester, a variety of sensors and actuators. There's over 150 different types that are then connected to the controller. Because they consolidated it into one controller, they were able to bring the domain experts closer to the system design to really focus on tuning this system. And then by connecting it out to the internet, they're able to do remote monitoring and remote software updates, as well as remote training and remote bring up with these systems. It literally is very impressive. They can just run the tractor from their facilities in Utah, completely remotely control it. And there's some gains that they can pass on to their customers. Okay? All right. So now I'm going to move on to London Underground. Yeah, please. So they released this product, again, about 1 year ago. We showed it at our facilities in August of last year, and they had shipped, we'll say, a fair number of systems. It was relatively new. I believe that the ProSlab released it in 2015, but it could have been late 2014. Can I ask if there's a question behind the question? Yeah, okay. So the question is, hey, 25 years ago we were doing elements of this, right? And that's true. And sometimes people talk about, I'm going to make a couple statements and I'll ask the specific question is what's happened that's caused a shift. Well, first, the concept of distributed control and data acquisition and data measurements and data logging has been going on for over 30 years, right? As we get into the Internet of Things and the industrial Internet of Things, there's a couple of fundamental shifts that are happening. One, there's an element of scale. These systems are getting deployed over vast distances. And there's also an element of systems talking to systems, okay? And the industrial automation space, the systems were very much in hierarchy. There was a central entry point into the machine, and then everything distributed from there. And that would actually stack up to the factory itself, right? It was a big pyramid, if you will. Now, the way, if we think about something as sophisticated as an autonomous vehicle, those are a bunch of independent systems talking to other systems in a huge network of systems. So that's a bit of a shift that's happening. Now, what's enabling these types of things to happen today? There's really 5 technology trends. You have, and it's all about reduction in cost. There's more processing, it's cheaper, Moore's law. Networking is becoming cheaper and the bandwidth is going up, and that includes wired and wireless. We also have sensors that are reducing in price. And then if we get into the consumer space, charging and battery technologies have continued to get better. And then the 5th one, well, open source plays a big role. The 5th one will come to me. But those 4 are really big drivers, right? Lower cost sensors, lower cost processors, better battery and charging technologies, and more bandwidth. And the tools are also getting better. That's another piece. So this whole system was designed by just a handful of engineers. It wasn't a big team. And so the team was working at a higher level with higher level software tools. They're programming processors and FPGAs and connecting to the network. And they're building everything on top of a platform. So they could focus almost all of their energy in this domain, this sort of complex control domain, where all their innovation went. And if we go back to 20 years ago, a lot of innovation would be happening on this side. And a lot of innovation would have to be happening on this side just to pull it off. And if you could think back to that data logging ocean floor system you did 25 years ago, how many people were involved, what were some of the technical challenges, maybe we could talk about that in the break. But thank you for the question. Yes? It's basically, and again, I wasn't on the design team, right? So I don't know all the details, but the sense I get from talking to Steve Aposhian, who's the technical lead on this thing, and the founder of the company, is it's just optimizing the system to the sweet spot. So they're not overworking the systems. Everything is very, very well tuned. And also the fact that they're using a hydrostatic transmission, that gives them, analog control of power being pushed out to the cutter and to the stacker. So it's not just on, off. They're able to really tune the speed at which things operate. So it's the level of fidelity they have in the control system that allows them to optimize the fuel usage. Did I answer the question? That's right. And so they provided, a lot of this stuff came from a platform. All of this came from a platform. They're not, LTE experts, right? They added the value here. So they are the ones that optimize the fuel usage, right? They're their control expertise of the system itself. Yeah. All right, so now this is another pretty interesting application. London Underground. How many people have rode the trains in London? Yeah, I happen to go to the pub or the soccer match, football match, or get back to my hotel. Okay, so this one particular line in London Underground is the Victoria line. And there's some statistics up here on the Victoria line. 213 million passengers ride this line every year. They run 33 trains per hour on this line. And the train itself is a 45-kilometer tube, the Victoria line. Okay? A bunch of stops along the way. Now, on all the tracks, to run their trains at that rate, you have to have systems in place to keep it safe. Because if you have a train that's running every 30 seconds through these particular train stations, there's the risk that a train could be on the track and another train could run on the same track and you could have a collision. So along the tracks, there's these systems that are called track circuits. And the way the track circuit works is there's a signal that's sent across the track that when a train hits the track, it shorts the signal. So the receiving line sees the signal go to 0, and then the receiver knows there's a train on that track. As the train moves off, the signal gets through, train moves on to the next track circuit, signal drops to 0 because it shorts across the wheels of the track, and then continues down the line. Now the system is designed in this way that if the track circuit is delivering a voltage of 0 on the receive line, the assumption is there's a train on the track, whether it's doing that for any reason. So the system fails safe, right? So if the transmit thing broke, the assumption would be there's a train on the track, stop the trains. So what happens, this is the interactive portion, what happens if a track circuit breaks? The trains stop. That's what happens, right? So there's not a collision, the trains stop running. So if I'm trying to get home to my kids, or try to get to the pub, or wherever, to the theater, I'm going to go see Phantom of the Opera, or whatever, and the trains aren't running because a track circuit broke, and I'm a consumer, I'm not going to be happy, because I'm stuck on the train. It's going to lead to ill will, even though that was a architectural choice that was made for my safety and the safety of all the riders. So engineers at London Underground realized that one of their biggest problems was failing track circuits. And so they implemented a system, or had the idea, if we could implement a system that actually monitored the track circuits themselves and help us determine when they are going to fail, and we can maintain our track circuits better, we'll have the trains running more often. We'll have less train stoppages. So that's what they did, okay? So they ended up deploying systems that, again, acquired analog data. They implemented a particular system, 14 monitoring stations across the 385 track circuits, okay? And each one of those monitoring stations has 128 channels of RMS voltage and frequencies at every one of the monitoring stations. That maps to 32 terabytes of data being acquired every day. Okay. And through that, they can determine the overall health of the track circuit. Now, it would be absolutely, well, I was going to make an extreme statement. I'll say that it's unnecessary to transmit all that data back to a centralized location and store it. So what they do is they do analysis at the monitoring station itself, and then they only send the most relevant information up to the central control station around the health of the track circuit. Okay, so they decimate that data down to just a fraction, a small fraction of the 32 terabytes a day. Okay. Now, by doing this, they were able to come up with techniques to determine the track circuits were failing, and by comparing the uptime of the rail system on just the Victoria line, because that's the only place they've implemented it. It's one line in London Underground. And compared it to previous years, they've actually regained 39,000 customer hours. So those are people that, 39,000 hours of people not sitting on a train that wasn't moving because of a track circuit failure. And it translates into 350,000 pounds of little rail tickets, right, because those trains kept going. And this particular system, again, it was acquiring data, voltage, processing that data, doing analysis, predictive maintenance at the edge, and then passing information up. This was simply done by a handful of engineers that saw a problem and just dove in and tried to solve it. Okay? And when they were building this thing, they didn't know they were building an IoT solution. Right? But it's really what it's turned into being. Now I'm going to build out a visual that's very similar to the one we had before. Do it very quickly. So the integration of 30 to 32 track systems per monitoring system, or track circuits per monitoring system. They had no idea what type of measurements they were going to have to make and what type of analysis they were going to have to do to determine the health of a track circuit, because it had never been done before. Nobody had ever done it. So they got benefits of having flexibility out in the system, so they could change things on the fly and be very much in the software domain. And then, continuous monitoring, decimating data, and only sending the most pertinent data on to the centralized controller to do historical logging and maintain the health of the track circuit. Now, there's one other example that I'm going to go through, and I'm not going to go through step by step like I have in the interest of time. I'm going to talk about it at a higher level, but before I build this out, I'll speak to it at a high level. Now, some of you may or may not realize that, I'm sure you all realize that especially if people live in California, that the amount of power consumption varies throughout the year. In Austin, Texas, of course, everywhere it varies. If it's hot, people run air conditioning, that puts a higher strain on power infrastructure, and the whole power utility needs to build to that peak demand. Now, if you're in an area where power is not as abundant as it is in most of Europe and in the United States and in other parts of Asia where power is abundant, if you're in other parts of the world, you may not have reliable power. And the infrastructure is old and very expensive to change. So what Innovare has worked on is load balancing techniques where they can get large power consumers to temporarily reduce their power consumption so they can serve more, the utilities can serve more homes, more businesses, given the infrastructure that's available. So say, hey, big power consumer, please turn off half your chillers for the next 2 hours because we can't provide you that much power, so we can power this rural village out over here. So in India and South America, where their customers are primarily. There's a lot of sensors and analysis that's happening to get all this data, and then decisions have to be made back at a centralized location. So if I build this out, it's high quality measurements. There's a small company trying to get to market quickly, and then they're able to do load balancing on the grid. Now, it's a third example. It's grid related. There's a few others we could show. But what you've noticed is this visual has appeared 3 times. It's sensors, it's processing at the edge, and then there's passing the data on for additional computation and visualization into the IT infrastructure. Okay, and this is across agriculture, smart grid, as well as transportation. All right. Yes, question? Mm-hmm. Yeah, so security is absolutely paramount, right? So the techniques that we use and our customers use is there's a level of authentication between the enterprise system as well as the thing that's out there on the at the edge. And then, of course, secure data transport is used, whether it's a secure version of MQTT or AMQP is used in the data transport. One thing I'm going to show in just a minute is some techniques to actually make the things themselves smarter so they can help participate in the securing of the system. So adding some level of diagnostic and we'll say intelligence to the systems themselves to prevent the types of attacks that happen, such as the Stuxnet virus. Have you guys heard about Stuxnet? People are nodding. So I'm going to talk about that. Now, I don't think the security problem is solved. I don't want to make light of it. I think that's probably the most important problem that needs to be, we need to have continued work in this domain of security. I myself and my organization we're not security experts. What we're going to do is work with companies, such as Cisco, Intel, GE, Infineon, and understand what the right best practices are, and that's one of the reasons that we're IIC members and participating in these test beds, so we can implement these secure solutions and learn and then bake them into our products. But your question is very valid. Security is absolutely critical with these systems. Yes. So specifically on Firefly, is that the question? And this one here. So the question was, okay, we have 3 different case studies. We can imagine that the security requirements are different. If we think about London Underground, they probably have some level of air-gapped security where their network is isolated from the outside world. You could argue whether or not air-gapped security is sufficient or even sensible in today's day and age. But again, without me knowing the details on the OT side of these systems, it's hard for me to, the answers I will give are me making leaps, okay, using my best judgment of my understanding. I do believe, go ahead. Related, okay. Okay, so if we think about reliability of the network, okay, so if we think about Firefly systems, which is the agricultural system, if the network is unreliable, all they've done is they've lost that remote connectivity to the system, so they can't get predictive maintenance equipment or predictive maintenance information, and they can't help the farmer that's running the piece of equipment. The equipment doesn't have to be connected to run, right? So there's a farmer running the thing. It's just like if a Tesla lost connectivity, it would still run, right, or anything else, okay? If we think about London Underground, if their maintenance system stopped working, they just go back to where they were a year ago, where their track circuits were failing more often than they would like. So nothing dangerous has happened in either one of those cases. Now, if we think about the Innovare system, they're actually in an automated fashion telling large consumers of electricity, organizations like factories, to stop consuming power. There is a higher level of threat and risk. And my understanding is they have taken steps and have worked with the utilities, which are really the folks that have the liability, to get to the point where systems are robust and secure enough to counteract the level of risk, so people are comfortable with that. But I think your point is very valid, that security network robustness and network security are going to dictate what level of control we're going to put across that network. All right. Great question. Thank you for helping the monitor. Another question? Yeah. Yeah, okay, so I'm trying to walk that line between, I don't want it to be an NI thing, because I think the customer applications are interesting in and of themselves. Now, what we provide is we provide high-level software tools, the processing system, and all the I/O. So, for instance, This is our hardware. It's a processor plus FPGA plus I/O. And then our software is used to do the advanced control and analysis on that processor and the FPGA. And the software environment is called LabVIEW, which is a graphical programming environment. You can also run C or Python or whatever, but most of these customers are using LabVIEW, the ones I've shown here. In the case of Firefly, if I go back, or we'll just go back to London Underground, this is more of a packaged version of that same architecture where the modules are I/O modules here, where people can hook sensors and actuators, our communication protocol like CAN or LIN or FlexRay, which would be something to be used to automate a machine. And then there's, in this particular system, there's a dual-core Atom processor from our friends at Intel, and then there's a Xilinx FPGA in the backplane. All that's programmable. Now, everything when we provide a validated, highly tested real-time Linux distribution, we call NI Linux Real-Time. It's our own distribution. And so we provide the fundamental communication protocols in the IT domain as well. Things like AMQP, MQTT. We have other data transfer mechanisms that allow people to connect in an IT-friendly way up to the enterprise. Did I answer the question? Okay, great. All right, so now shifting gears a little bit. Okay, so this architecture has appeared multiple times. This idea of things with sensors and actuators, multiple processing systems with I/O that are all network connected and then hit the edge and go back to some form of IT infrastructure or the cloud, whether that's through the AT&T LTE network or it's through the internet or the network that's there at London Underground, or if it's through some other networking mechanism in India or South America. Okay. All right, so this architecture that I just showed almost is exactly what appears in the IIC, the Industrial Internet Consortium, Industrial Internet Reference Architecture. This visual is from that document. You can get that online. It's called the IIRA. Just search for the Industrial Internet Reference Architecture, IIC in Google, you'll find it. So these letters up here. This is a particular architecture which is the most common that I have seen, not only from us, but from other people that are building test beds and implementing systems, which is called the 3-tier architecture. This visual we made based on that picture, just so we had a high-res version. Copying a picture out of a PDF file, putting it on a slide looks like garbage. So we went through and recreated it. So things may look slightly different from a font type, or a color might be a little bit different, but it's intended to be as true as we could to that system. And here we have the edge tier, which is where our measurement and control hardware as well as the processing is happening. There's this concept of an edge gateway. That's the device that allows you to connect to the enterprise. In our case, our device is the measurement and control system as well as the gateway. Right? There's not a separate gateway, except for in the example of Firefly. They're using that LTE gateway from AT&T, or one of AT&T's partners. And then you have the systems management and analysis happening at the platform tier, and then there's the business tier or the enterprise tier, where you're doing higher level control and automation. So it's somewhat interesting that the people who, and I wasn't involved in writing the reference architecture. We were sort of, we were reviewers because everybody at the IIC could review it. Everyone could read that 250-page document and give their input. But other people are seeing the same architecture, and they baked that in, and then we looked at it and went, man, that's exactly what we're seeing again and again and again. Yes, question? Mm-hmm. That's correct. And just to be clear, okay, so the question was, hey, you know, you talked about 3 examples where there was data processing happening right at the edge, but hey, there's a lot of examples where you want to move a lot of that data or a subset of that data up for additional processing. Okay, making sure. All three of the examples I showed, that is exactly what's happening, and I apologize for not being clear. So there's significant amount of data reduction and analysis happening here, but most of the advanced analytics is happening at that enterprise tier, that platform tier. So just let me finish this thought. So in London Underground, determining whether or not the track circuit was failing was not happening here. All the data was processed and then it was handed up a level, and that's where the final determination analysis was being done at a higher level. Same with Firefly, they would push their condition monitoring information up to Utah, and that's where they would do the trending and determine, hey, vibration's a little high on the cutter, or the conveyor is consuming too much power. Okay, you had a follow-on question, clearly. Yeah. Oh, this way. Oh, that way. So one customer that we talk about a fair amount, and they've gotten up on our keynote stage a few times, is Duke Energy. Are you guys familiar with Duke Energy? They're the largest power provider in the United States. So across most of the southern eastern coast and into the south, they're the power provider, and into parts of the southern part of the Midwest. Okay. The way they operate is they do data collection and they do analysis at the edge, but then they move everything up to the plant server for storage, because they're trying to build patterns, they're trying to learn. So they do analysis at the edge, but then they push the analogous data as well as the raw data, all of it, up to the plant server for learning. But because they do that, they have a very distributed enterprise solution. Every plant has their own plant server. And so they have elements of sort of siloed data that you log into remotely. So that's an architectural decision that they've made for a variety of reasons. That's right. Yeah, so and it's really, how much data are you pushing across this pipe? Right? That's a really good point, really good question. They can. The practical issue that they face is some of their power facilities are in such remote locations. The spigot they have on those power facilities is very, very small. Now that's a time-bound issue, right? If we go out 15 years, these spigots will be bigger. We get Y-gig out there, everyone's going to have more bandwidth and they know what to do with, and then we'll figure out what to do with it all, right? And then we won't have enough bandwidth. But the rules will change over time. But they have a blend of practical as well as sort of risk management decisions. But you're right, that conceptually there's no reason why they couldn't aggregate everything in one location, that they build out that infrastructure. Great questions. Thank you. It's a great transition point. I'm going to ask this question, then we're going to get into exactly that point. Okay, so first I just want to make sure we're all on the same page, that sometimes using an operating system like Windows and using a processor alone may not be able to get the job done. Have we ever had a processor-based system fail us? You guys ever had a processor system fail you in some way, shape, or form? Yes, of course. Of course we have, right? Okay, and so sometimes maybe a PC can't get the job done. Sometimes you may, and that's because there's all sorts of stuff happening on a PC that you don't know about, you can't control. This is my particular processes are running. This is a colleague of mine, member of my team, Sanina. This is her Mac. There's all sorts of stuff happening. And, don't look too much because there might be something there, people to see is running. I don't know. But those are literally copy paste. But we also know that processor-based systems are doing amazing things all around us. So I don't want to malign the processor. So as we said, there's roughly 100 processors inside of a contemporary BMW or Tesla. It's interesting that Joe mentioned this as well. All these financial transactions are happening in the stock exchange are done with processor-based real-time systems. And then primarily robotics is done with processor-based systems with either DSPs and FPGAs complementing them. Okay. So as we talk through this issue of hierarchy or hybrid systems, it's important to take a step back and think about time. Time. Okay, it's just a dramatic pause. Why am I not advancing here? Okay, I'm going to probably go like 7 slides. I think my processor system just failed me. I literally got a wait, got some sort of thing. Okay, so this visual here, I want to talk about a couple of key points. Okay, so if we think about time, sometimes it's hard for us to get our minds around time. Okay, and there's also the concept of determinism and reliability. If we think about something like an eye blink blink's in roughly 300 milliseconds. It's 300 to 400 is what the literature says. And it's a pretty deterministic system. I don't know if any of us have ever had an eye blink fail in mid-blink. Typically, it starts and it completes the process in a very reliable, very deterministic systems. But a performance vehicle, like a Formula One racer, in about 1.7 seconds, it can get 60 miles per hour. And like a Porsche or a Tesla can do it in about 2.5, 2.8. Okay. That's not completely reliable, right? We can imagine an engine blowing or something else happening, right, in that process. And we've all seen the just painful pictures of the world-class athlete, collapsing before the edge of the finish line, right? But it takes 3 to 5 minutes to run a mile. The fastest people in the world can do it about, the world record is what, 3:40, 3:50, something like that. But there's certain things, and certain things you just can't rush, whether deterministic or not. You can't cook a cheesecake in roughly less than an hour. And if you try to do it in 10 minutes, what you get is not going to be a cheesecake, it's going to be something else, right? And I don't know if anybody's ever heard the humorous, it takes 9 months to have a baby, and if you put 2 women on the job, you can't get a baby in 4.5 months. Some things just take as long as they take to get the job done, right? And probably the most deterministic system we have up here is light coming from the moon. It takes 100 microseconds for light to hit the moon and then get to us. It's pretty damn reliable, pretty deterministic. It's just happening constantly. And 1 microsecond is the amount of time it takes for a high-speed flash to actuate. 1 microsecond. All right, and the 3 milliseconds here, in case you're curious, that's the speed at which a fly's wing flaps. All right, now processing systems. What is happening here? Okay. This is mine, though. Yeah, it's weird. Now I'm actuating through the slides differently. I'm going to do this, and I'm going to do this. Okay, what slide are we on? 147? Around there? Yeah, I'm home. Okay, I'll just talk for a second, and then my processor system failed me. This is part of the presentation, actually. No, it's not. Okay, hey, we responded. Things should come back. Okay, boom. My machine's gone dark. So how many people know how to get to slide 47 in PowerPoint? Does anybody know this trick? Yeah, it's simpler than that. Okay, we'll let this thing come up. So the point to make about time and reliability is what we were going to see in a minute is different processing systems can take on different rates and reliability based on their fundamental architecture, the operating system that's running on them. So one point to make is with the Windows system, a PC can, in most cases, all kidding aside, it's pretty hilarious this is happening now, is a PC will respond in 100 milliseconds to a second in almost all cases. Great. Okay. Oh, good, I'm right on it, so we're just going to go like this. We're going to hope it happens here. Okay. So, responds in 100 milliseconds to a second in almost all cases, but it's never guaranteed, right? We could be screwing around with this for the next 20 minutes, right? And it's just the nature of the operating system. The operating system is very general purpose. It's intended to do a lot of things. It's intended to be easy to use. It's not purpose built. It's built for flexibility, right? But then if you get to a real-time operating system, you can run real-time control loops with a processor-based systems in the 20 kilohertz range. So every 50 microseconds iterating on your loop, and you can guarantee determinism based on what operating system you're using and what type of processing that's happening on the system. This should actuate. This is great. And so then you can have some level of guarantee, but still processor-based systems still crash, right? There's still some risk of crashing. Now, the next level beyond that is implementing logic and hardware, right? Using something like a field programmable gate array. How many people are familiar with the concept of an FPGA? Most people. So basically, a field programmable gate array is a hardware instance that can be configured, if you will, or programmed to perform a particular function by organizing DSPs and connections and logic and memory, and then it operates over and over again reliably like gears of a clock, right? There's no operating system that's supervising the code execution at all. And there you can get control loops in the control domain running at in 25 nanoseconds reliably. You can actually run FPGAs much, much faster than that. But most of the time when they're implemented for control systems that interface with the physical domain, that's a similar rate. So that's significantly faster, 4 times as fast as that high-speed flash. Okay. Now we're going to hope that I can advance. Oh, so this is your point right here. Okay, look at that. Okay, so it does make sense to think about time and reliability as we build out these systems, and when you need to make decisions quickly, such as controlling the cutter and the conveyor on the Firefly system, doing that right at the edge, right? They're running their control loops in the area of hundreds of microseconds rate. But if your decisions can be minutes or hours or even days, like if you're doing something like predictive maintenance of a wind farm, you don't need to make decisions in the milliseconds or microsecond rate. You have a significant amount of time because the mean time between failure on these mechanical parts is months or years. So you have time. Okay. So down here you can be at the microsecond reliability, and as you move up, sort of time moves. And there's another element to this. It's not just the processor and the operating system, it's also the network, right? Network reliability and network bandwidth help or put some limitations on what's possible in these types of systems. In the case of Duke Energy that we talked about, they just don't have the network infrastructure to include the cloud in their solution. And if you're out at sea in a sea-based wind farm, it's also a challenge, right, for those systems. Yeah. Okay. All right. So now trying to advance again. Okay, here we go. Now I already talked about what an FPGA is. This visual was intended. That's a Xilinx part called Zinc. It's an SoC that's got an FPGA on it as well as a processor. But sometimes people think about FPGAs as just simply being logic and interconnects. They've really evolved. In the case of contemporary FPGAs, they do have hard DSPs on the FPGAs themselves that can handle floating point data pretty well. And then there's a bunch of interconnects and logic that are running in this dedicated piece of hardware. And for those of you that are more graphical in nature, if we think about this, as I said, this 40 kilohertz control loop rate on a processor-based system, if you push that out to the FPGA or to that hardware implementation, you get a 40 megahertz control loop implementation, so a factor of 1,000 times faster. Okay, so now I want to talk about this concept of processors plus FPGAs a little bit and why people might want to bake one of these things in. Because it will add some cost, and it will add even more than cost, it adds power consumption. That's probably the bigger sin of the FPGA is power consumption. But there are a lot of benefits. So I'm going to walk through 3 really nice capabilities. One's co-processing. I'm going to show a vision example, co-processing. Then the other one, we'll get to that in a second, is going to be more about advanced diagnostics. So here's an example of a fundamental system where we have a camera hooked up to a real-time operating system that's doing image processing. The particular image that we're going to be looking at is molten metal and looking at the properties of the metal. Okay, just as you see the picture, that's what it is. I don't want you guys going, what is that? What is that picture? That's what this thing is here. Okay, so you can, of course, do this blob analysis, as it's called, which is a binary form of image processing, using a processor-only system. And that's the way a lot of it's done. Okay? But if you bring an FPGA in as a coprocessor, you can get some really nice benefits to the system. So if we take a look here, this is now the molten metal. Okay? And you can see here are these blobs or these artifacts as the metal's going through its transformation and melting, that it moves from this grayscale domain. The image itself gets crisper through a process called convolution, and then it gets thresholded into a binary image, and then morphology happens and filtering happens to count the blobs of a particular size. It's a pretty common vision technique. It's been around for 20 years. Now here, if we look at a system, if it's just using an Intel Atom processor to do the processing, you can do 23 frames per second. If you instead use an FPGA for the convolution and the thresholding step, thresholding's easy, but you do it in the FPGA, so why not? Then you're able to do about 4 times as many images a second. You go to 98 images a second. And that includes the round trip of pushing the image down to the FPGA and extracting it. And if you have to do the convolution step 10 times, because you really need to crisp that image up, which is also common, the host system can only do 1.5 frames per second. But the FPGA system, it doesn't change, because the FPGA is not your bottleneck. You can do more and more convolutions and keep up with the processor. Does that make sense? Did I lose people? Okay. So again, it's even though there's the overhead of pushing the data down to the FPGA and bringing it back up, it still gives you significant net benefits. And this is pretty new. We've been doing vision as a company. Actually, I worked on vision in the early part of my career, and it's been about 19 years, 20 years that we've been doing vision at NI. And bringing FPGAs into the image processing has really gotten center stage about 18 months ago. So it's pretty new. And we didn't really know, even though we had FPGA-based systems, how much benefit it'd be able to give us. And we've been pretty excited about the type of gains we've been getting. Okay. So now I want to talk about another concept of how the FPGA and really system design is evolving, and the concept of digital twins or model-based diagnostics are these 2 terms that are used. So what we're going to do is we're going to talk about a very, very simple system. Okay, it's the control of a thermal chamber. Think of it as a fancy oven. You can control a fancy oven. I've chosen the thing to be a thermal chamber because it's easy to understand and people do it all the time. Okay, we are going to talk about taking the concepts I'm going to show here to more complex systems in a few slides towards the end. So I'm not here to talk about how to do the control of an oven, right? Because we all get that. Okay, so if you start in the end goal, you're going to have maybe one oven or lots of ovens that are controlled by a controller, and then you have some centralized supervisory control system that's maybe in the cloud or on the plant side that sends control signals down to your controller through MQTT, sort of an IT protocol. Okay. All right, so when you start, you don't have the oven that you're controlling, so a model gets made, either by the developer or by another member of the team, and then the developer starts developing their control code on a workstation. They get the control code so it's working reliably against the model, and they can put it through several test vectors on their PC and get everything working reliably. And then a common step that's done very comprehensively in transportation, whether it's automotive, rail, or air, there's a step where the model is put on a controller and makes the plant, and the control software is also put on the final controller, and those things are connected together to test the controller and the control code against a plant that's running a software model where faults can be put into the system. So what happens if the particular system isn't operating the way you would expect it to? How does your control software deal with those fault cases? And this is called HIL testing, or hardware in the loop testing. Okay. I'm not sure if that concept's new to everybody here or if you've heard about it, but it's extremely common in automotive, rail, and aerospace, and it's becoming increasingly common in white goods and power electronics. You know, test things up before you actually hook them on the grid. It'd probably be a pretty smart thing to do. All right. All right. So then when you're done, you got your control code, and you've connected it to your real thermal chamber, and everything works great. But you have this model that you've built that you use during your HIL testing. So why not use it? You have it, use it. Now, can someone, you also, yeah, you connect it up and you're doing your MQTT and managing it. That's all great. So you have this model, and you have this model, okay, and you might be able to use this model to help you determine when the system itself is not working correctly. So we've come up with 3 somewhat easy to understand but manufactured fault cases. The heater breaks. Let's say in this particular oven, the heater breaks a lot. Okay. Another thing that happens is the heater gets stuck on. You could say, well, why are you using that heater supplier? You need to change your heater supplier. Okay, that's not the point. The point is these could be 2 common faults. The heater gets stuck on, or the heater just completely fails. And how can your controller know that that has happened? Okay. And it's one easy technique is to actually be testing against the model at all times. And if the model deviates from the actual thing you're controlling, then you know something's gone wrong. And then there could be a whole host of other unpredicted failure modes, including being hacked. So another thing that we've looked at is, let's say somebody hacks in and changes the temperature value that's being measured inside the controller or inside the oven and passes a different temperature value back to the controller. What does the controller do? Okay. And I'm going to switch over and show this in a demo. So wish me luck. My PC's been working great, so hopefully this works really well. So we're going to slide this over. We're going to slide this over. This is gone. I'm going to be more aggressive with my shifting. Okay. So now, for those of you that are familiar with the Stuxnet virus, really what that thing was doing is it was changing values and registers on PLCs, right? So it was changing things like temperature values or other feedback values, which caused the control systems to behave in an unpredictable way. So let me get in here now. It should come up. Oh, you know what's happened now. This is just killing me. Okay, I'm going to go into here. I'm going to kill it. Because now it's off screen, because it's gone back to now where it's duplicating and my stuff's off screen. It's great. Just do this here. Yeah, maybe I'll board on this. Now, if you think about what can happen if somebody hacks in and changes your system, and it's something like a temperature, right? If they say, if you're trying to drive the temperature to be 40 degrees C or 50 degrees C, and they tell you it's at 20, you're going to turn the heater on. And you're going to run that heater indefinitely because you'll never hit your set point. That could happen. You also could be saying, it's 60 degrees, it's 20 degrees, it's 60 degrees, it's 20 degrees, and cycle that heater and break it, right? And a heater, that probably wouldn't happen, but there's other things if you're sitting there pounding things on and off, and that was another thing the Stuxnet virus did. It hit valves. It went bam, 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 bam on valves, and would break them. You move them, shorten their life, you know. That's another thing that can happen. And we can imagine, let's say it's not a heater, it's a tank. You can imagine if you say the fill level's here, a pump gets turned on, the fill level never moves because it's been spoofed, the tank ends up overflowing. Right? That's another thing that could happen if it wasn't a heater, it was a tank. Okay. Okay, I'm about ready to abort. Okay, I'll maybe come back to that in just a second. And where are we from a time check? So I have 10 minutes. Okay, this will be perfect if I can get to work. I'm going to be severe. What's going on? Okay. I'll come back and I'll show this thing right at the end. Okay, yeah, my PC is really not behaving well. So I'm going to resume slideshow and just move forward, because now I can't even get my start menu to come up. So something's going on. Maybe that's Stuxnet, who knows. Okay, so here's the trick. Did it work? Yes. So if you just type in the number and hit enter, you go to that slide when you're in presentation mode. So many of you probably knew that. Okay, that's my end. Let me go back. All right. So when I get finished going through my slides, I'll take maybe the last 5 minutes and show that demo. I'll just get out of this PowerPoint completely and show it. Yeah, I apologize for this. Now, if we think about the concept of the heater, it's a pretty simple system. It's pretty simple to model, but we actually are seeing people do significantly more sophisticated systems. Oh, man. Wait for system to respond. Okay, there we go. All right. So things like doing predictive maintenance or condition monitoring, where you actually take a system where you use analog data to monitor your system and determine when it's moving out of its acceptable operating zone by actually having models on the system and performing condition monitoring. You also can do sophisticated things by having FPGA systems sit alongside distributed control systems. This particular visual here is actually work that's happening at Oak Ridge right now. Dr. Buckner and his team is working to simulate large portions of the eastern grid and simulate it in real time. So the components that are on the grid, to determine its behavior in real time, to do a variety of things, to help predict faults, as well as to determine if there's anything going on that shouldn't be going on. Today, they've implemented a system based on FPGAs that completely simulates a microgrid that has quite a few components on it. And this visual here is to show you put the grid, you simulate the entire grid infrastructure, as well as all the control logic in the FPGA, side by side with the real system, and see how behavior changes over time. The current system that they have deployed and they're using is 80 FPGAs in parallel exchanging data using peer-to-peer streaming. 32 gigabytes per second is being computed in this system. And it's simulating 2 power grids, 80 microgrids, 80 distribution lines, and it's actually 480 three-phase inverters. They just scaled it up since this slide was created. All of that is being simulated. The control code, as well as the components themselves, are all being simulated. And then they have a physical instance of a low voltage version of the grid that they're testing things against. It's pretty exciting work. And it's actually faster than real time, but it's real time. Simulation's happening in real time in lockstep with the microgrid. It's exactly right. And you can actually run these types of grid simulations faster than the response of the real system. And one of the reasons for that is the grid is very large, right? So there's propagation delays, and the FPGAs are in very close proximity to each other. And there was a paper that was just recently released. Some of this information is going to be shown at a supercomputing conference coming up in Seattle in November. But it's pretty exciting steps forward in this sort of digital twin technology, or digital twin approach. Okay. So now I'm just going to say a few words about systems management. You know, you asked how is NI getting involved in this. You know, one of the things that we've continued to learn over time, and people don't think about it, this room probably does, but once you go from having 1 or 2 or 10 or 20 systems deployed on your factory floor to 2,000 or 20,000, systems management becomes a bear, right? We've come up in a world where our customers were doing tens of systems. Now they're doing thousands of systems. So we're using a technique where our systems communicate back using AMQP, and we've standardized on SALT as our systems management framework. You know, have people here familiar with SALT? It's one of the options. It came out of the IT space, and we did a sort of technology exploration, and that's what we're using. There's free versions and open source versions, but then there's also, of course, paid for versions. You know, not that different than Linux, right? You can get more validated, more hardened versions. And then all the information is brokered through a message bus using AMQP as a way we've implemented things. So there's the controllers themselves, whatever information they want to send up. There's these agents that package the data up into AMQP packets, and then pass that up to the message bus that hands that off to different services, whether they're customer-written services or services we write. And that's how we handle the systems management challenge. And this is relatively new stuff for us. Our first implementation is more condition monitoring focused, but now we're broadening that more and more. Okay. And then the last piece, just to make you aware, and then I'll try to do the demo again, is moving large amounts of analog data around and keeping it organized is a challenge. The organization that has really shared this challenge with us is the automotive industry. They have all these regulatory requirements to do all of this testing, and the data gets organized poorly, and it sometimes forces them to go back and retest because they just simply can't pull the data out of old systems. Okay, so there's again, an open standard called TDMS, which is a file format that's sort of self-documenting file format that uses an XML header and then binary data underneath to move around large amounts of waveform data. Because most of the other standards are about, you know, floating point values, scalar values, or collections of scalar values, not waveforms that are associated with single channel. Sort of a different concept. Here's an example of it mapped to a cell phone test. This hierarchy. Okay. So with that, I'm going to close out a PowerPoint and try to show that demo. And if I don't get it to work, I'm just going to be sad, and I don't want to be sad. So I'm going to try to do that. Any questions while I'm relaunching this thing? Or comments?